Hello everyone, and welcome back to the only channel where you can get an underage nerd to teach you electronics. Today, it's time for variable resistors, which are insanely useful for a wide variety of things and will enable you to do so much cool new stuff with your Arduino. Let's get right into it! First of all, what even is a variable resistor? Well, as the name suggests, it's a resistor that varies according to something. A bit vague, I know, but that's because there are many types that vary according to many different things. Let's look at them. In a typical Arduino kit, you'll normally get a photoresistor, whose resistance varies with ambient light, so it'll let more electricity through it the brighter it is, a thermistor, whose resistance varies with temperature, and a potentiometer, whose resistance varies with the angle its axle is rotated. There are a bunch more types, but these are the most versatile and easy to use. Let's start with the potentiometer, as it's the simplest among the three. I briefly went over it in the joystick video, but the way it works is it has a conductive but resistive track and a wiper connected to the knob. Electricity flows through the track and then goes into the wiper and out the middle pin. However, as the track is resistive, the further it has to travel through it, the less voltage will come out of that pin. So if you position the wiper at the start, the full voltage will come out of it. If you position it at the end, the full resistance will apply, while if you position it in the middle, you'll get a voltage in between. There are different potentiometers with different resistance ranges, but the most common ones are 10 kiloohms. And they also come in different form factors like these linear sliders, but it's the same working principle. Now, you might be thinking, but wait a minute, if a potentiometer is a resistor, how can it make the voltage collapse to zero at the far end? Because if I connect a 10K resistor to an LED, look, it lights up. You are a liar. This is potentiometerist propaganda. No, listen. A potentiometer effectively acts as two resistors in series, one before the wiper and one after. And this just so happens to be the circuit for a voltage divider, where the ratio between the first resistance and the second one defines the output voltage in the middle. To test it, you can get a component like a buzzer, a motor, or an LED, although in this last case remember to still add a resistor. Connect one side to ground like normal, but on the 5V side, we'll place our potentiometer first. Socket the 5V and ground, connect them to the pot's side legs, and get a wire from the middle leg to, in this case, the LED, with the resistor of course. Now, as you turn the knob, the LED's brightness increases and decreases smoothly. This is very useful when you want to modify current freely without even having to use an Arduino board. However, we can also use it as an input for code. To do this, we'll simply connect the middle pin to one of the Arduino's analog pins and we're good to go. Now, if you watch the joystick video, this is going to be quite familiar because, as I said, the joystick uses potentiometers. So, in the void setup, first of all, what we're going to do is, because we're going to be printing the values onto our serial monitor, we'll do, as always, serial.begin, just 9600, and then, of course, we'll need to set our pin mode for our analog pin. So we'll do pin mode A0, because it's analog pin 0 for me, and input. So that'll be our analog input pin. Now, in the void loop, all we're gonna do is serial.println, and here we can actually just put directly the analog read A0. So yeah, really similar. This will just repeatedly print the value that our analog pin 0 will be reading from our potentiometer. So let's upload it. If we now open our serial monitor, we should be able to see our values coming in. As you can see, my potentiometer is at the lower end right now, but if I now turn it, I should be able to get it all the way up to 1023. So now you have this really useful way to get values into your code. You can modify it externally and then do whatever the heck you want with it. Alright, now on to the thermistor. There are actually two kinds, positive temperature coefficient and negative temperature coefficient, but PTC thermistors spike up after a threshold and are thus no good for measuring, so we'll be focusing on NTCs. These are simply made of a semiconductor and take advantage of its fundamental working. As you heat up such a material, electrons get enough energy to move from the valence band to the conducting band, where they can finally act as carriers of electricity, and this means that the harder the semiconductor is, the more current can flow through it. Simple enough. Now let's use them. To wire a thermistor, we'll connect 5 volts to one leg, our analog pin to the other one, and we'll actually need to connect that same leg to ground through a resistor. Otherwise, no current will be flowing because our analog input pin acts like an infinite resistance resistor, so no current can flow through it. And with no current, there will also be no voltage drop across the resistor. And remember, an Arduino measures voltage, not current. As for this fixed resistor's value, if you choose one that's different from the thermistor's rated resistance, you can actually shift its measurement range, as it's an exponential curve, and you'll therefore get more precise measurements in its steepest section. However, as the rated resistance is based on ambient temperature, if you're gonna be measuring anything close to that, you should choose the same resistance as the thermistors, so in this case 10 kilo-ohms. This isn't necessary for the potentiometer because we already have 5 volts and GND completing a circuit. Okay, so how do we code this? Well, here's where I'm gonna go and tell you that basically every other tutorial on the internet on how to use a thermistor is wrong. Why? Well, because they use the Steinhart-Hart equation. Now, naively, this would seem like the correct choice because the Steinhart-Hart equation is the one that gives the most accurate values for temperature with respect to resistance across a wider range of temperatures, but it depends on 3 constants, A, B, and C, which are completely different for not only each model of thermistor, but each manufacturer of each model, which means that it doesn't really make much sense to include them in a tutorial because it will be completely different for each person and you just have to measure them yourself, which is pretty hard. And I guess what happened was someone just posted their own on a forum and people did the easy thing, copied and pasted them into their tutorials, and now it's like everywhere and it makes no sense. So we're gonna use the beta equation instead, which is a simplified form which only has one parameter, beta, which you can actually get directly from each thermistor's datasheet. In my case it'll be 3950, but if yours is different, you just change that value and the equation will work completely fine. And it actually only deviates a bit from the Steinhart-Hart equation at like extremely high and extremely low temperatures, so for our case that'll be completely fine. So the first thing we're gonna do is introduce our variables. The first one will be our beta. Let's do B because I'm not gonna take out the Greek alphabet, and for my case that'll be 3950. If yours is different, again replace it with whatever your datasheet says. And now let's do float R for resistance and float T for temperatures. Remember, this will be decimal numbers. And now in our setup, as we're gonna use the serial monitor, let's initialize it as always, and let's also initialize our pin in input mode. There we go. So that's our void setup. Now in the void loop, here comes the juicy part because we're gonna calculate the temperature. But if you noticed, we calculate the temperature with the resistance. But we don't have the resistance, we have a value between 0 and 1023. So what do? Well, we rearrange the equation for the voltage divider, and instead of using the maximum voltage, so the source voltage, and the measured voltage, we use the maximum analog read, which is 1023, and the measured analog read. And this will give us that R equals the fixed resistance times 1023, and we'll actually add a little .0 here so Arduino knows it's a decimal number, not an integer, because here we'll do analog read a 0 and then -1. So the problem here is if we didn't add this .0, these are two integers, so Arduino would do an integer division, and this will be like around around 1. So it's just gonna round it up to 1 instead of our decimal, and we will lose like basically all our precision. So yeah, really careful in code in general actually, you gotta be very careful with floating point division. Yeah, we just specify, it's a kind of a little hack. We specify that it's a decimal, so it doesn't do an integer division instead of a floating point, which is what we want. And now, for the temperature, here we'll paste our little beta equation. It's really simple. We just have that temperature equals 1 divided by the inverse of the ambient temperature. And no, this does not assume we move to Mercury for vacation, it's just that it's in degrees Kelvin. Plus the natural logarithm of our measured resistance divided by the fixed resistance. And yeah, it's the natural logarithm because Arduino decided it doesn't follow the rules of mathematics, even though log is normally the logarithm base 10. Here in Arduino they decided they're special, and the natural logarithm is just log, of course, and divided by our beta. So here we get our temperature, and now we can print it with serial.print T. Although actually, this will give us the temperature in Kelvin, so if you're not a Kelvin enjoyer, before that we can do T equals T minus 273.15, and that'll give us the temperature in degrees Celsius. If you want it in Fahrenheit, well then you're out of luck. Serial.print T, and then serial.println, because it's in degrees Celsius, let's add a little degrees Celsius symbol here. And let's just add a little delay so we don't flood our serial output with numbers. And let's upload this. And as you can see, we are now getting our temperature values printed on the serial monitor. Right now, I'm at a mild 30 degrees. Comment down below what temperature you are at. And finally, let's look at photoresistors. These actually work almost exactly the same way as thermistors, just instead of heat giving electrons enough energy to jump to the conduction band, it's photons, light particles, that provide that energy. So the more light there is, the more current can flow, so the lower the resistance. Just like thermistors, photoresistors need a resistor to work properly. And as the function for a photoresistor's resistance is also nonlinear, although this time it's a power function instead of an exponential one, you could technically decide on its value depending on the light levels you'll be measuring. However, unless you're measuring laser light or trying to detect if a pitch black bank vault has been slightly opened, you'll probably be fine with a standard 10 kilo one. So, what we're gonna do now is make a little sketch that will give us our current light intensity. And it'll be measured in lux, which is basically the light intensity per area, which is what the photoresistor is sensitive to. 1 lux is equal to 1 lumen per square meter. So, the first thing we'll do is, of course, introduce our variables. And for the photoresistor, we'll actually have 2 parameters. One is, of course, the rated resistance, and for me that'll be 10,000 ohms, although in this case, it's the resistance the photoresistor will have at exactly 10 lux. And the other one is gamma. Remember I told you that the function for a photoresistor is a power function. Well, gamma basically tells you how steep that function is. It's basically the exponent of it. And for me, that'll be 0.6. These 2 values are always specified in any datasheet you can find for any photoresistor. So yeah, if yours is different, yes, you can just look at the datasheet and you'll easily get these 2 parameters. And then we'll just introduce, of course, our resistance and our light intensity. And those will be our 4 variables. Now in the void setup, just like with the thermistor, we'll just initialize our serial monitor and our pin. I also used a 0 for this in this case. And yeah, that's it. And now in the void loop, well, first of all, we need to calculate the resistance. And well, the circuit is basically the exact same, and so we can just use the exact same formula as we did with the thermistor. And so this will be that R equals our fixed resistance, so 10,000 ohms, times 123, remember to add that little 0 to make it a float, divided by analog read R pin, and then minus 1. And just like before, this will be our resistance. And now comes the equation. It's even simpler than for the thermistor. We just get that the intensity equals 10, because remember that the baseline resistance is defined at 10, already at 10 lakhs, times this is the power function, so this would be the base, and then a comma, and this is the exponent. So we are raising the ratio between this baseline resistance and our measured resistance to the power of the inverse of gamma, which, as I said, defines our exponent, and here it is. So yeah, really simple equation, in fact, and this will give us our light intensity, and that's basically it. We can already serial.print on intensity, and let's just add a little delay here as well and upload it. And so if we now open our serial monitor, we should be able to see our lux values. So if I now cover my photoresistor with my hand, as you can see, it goes to basically 0. And if I now get my flashlight and pointed at the thing, we can get, oh wow, that's a lot. Almost, yeah, about 1,000 lux. That's quite a lot. So yeah, you can now measure light for whatever purpose you can think of. That's really cool. So yeah, as you can see, as the brightness changes, so does the voltage across the photoresistor. What is this insanely cool looking gadget I'm using? Well, this is a current measurement clamp, and it solves a problem every beginner in electronics eventually runs into. Voltage is easy to measure. You just put your multimeter's terminals at different points of your circuit, and that's it. But if you want to measure current, you need to interrupt the circuit to make it go through the multimeter instead, and even then a multimeter can break if too much current goes through it. That is, if it's even feasible to interrupt the circuit in the first place, as sometimes you might be using connector types you just can't plug into a multimeter without peeling the wire. A current clamp, however, avoids every single one of these problems by offering a quick, contactless way to measure both AC and DC current. And this one, from the good old Medusae of course, can also fulfill all the functions of a standard multimeter, and even has a nice little flashlight. And as always, all while being cheaper than many clamps that don't even have a digital display. And if you want it, or any other gadgets from Medusae, for even cheaper, you can use my link, which you'll find in the description, and enter the code FLAMETHROWER at checkout. As always, thanks for watching, and please remember to like, subscribe with the bell on, and maybe leave a comment, as very few of my viewers watch these tutorials, and we don't want the YouTube algorithm thinking my channel is dead. I hope this video helped you, and I'll see you in the next one.